Hello, my name is Jonathan Newman. I am an OREU student research intern working under Dr. Raimundo Arriabe. I'm very grateful today to be sharing some of the research work I have been conducting under the guidance of my graduate mentor, Brent Vela. Today, I'll be discussing my work on polygonal alloy space embeddings for visualization of high entropy compositional property spaces. High entropy alloys are a property class of materials for materials research. HEAs have an extensive use in fields such as nuclear or aerospace. By definition, they are comprised of 4 or more elements with concentrations ranging from 5 to 35 mol%. Because of the vastness and diversity of the HEA space, many alloys with attractive properties have been discovered. Some of these attractive properties are seen below. The problem I'm addressing is how to visualize compositional property relationships in high-dimensional spaces. In terms of plotting characteristics for a binary alloy system, an XY coordinate system is used. For ternary systems, you could use a Gibbs triangle, while quaternary systems require a Gibbs tetrahedron. This projection, however, is difficult to show on a flat page. In 5D plus systems, we run out of dimensions to use. We rely on UMAP and t-SNE, dimensionality reduction techniques, to overcome this issue. Here we see how these projections would look for ternary, quaternary, quinary, and centenary systems. Uniform manifold approximation projection is a data dimension reduction technique that plots higher dimensional points on a 2D space. Other implementations of UMAP plots, while still have the same algorithmical premise, leads to points being projected in an unintuitive manner. Data can be seen clumped in groups. In our case, we provide the entire chemistry space for embedding. Our method of UMAP projects HEA spaces in an easily interpretable polygonal shape. Each vertex corresponds to a unary. For example, if the HEA has 5 elements, a pentagon shape is formed, and etc. The closer you get to the shape's vertex, the more the alloy is rich in that element. Towards the center, the composition is more equimolar. We then plot properties over these embeddings to show how these properties change with composition. For example, these graphs can be interpreted like in the figure below. The leftmost graph gives a reference of how elements are distributed in the projection, while the 2 graphs to the right portray the properties. Alloys near the tungsten-rich corner of the UMAP are colored more green, representing more tungsten content in these alloys. Likewise, the middle graph depicts configuration entropy. My project goal was to expand the capabilities of the UMAP projections. First, I'll show a portion of the work focusing on what I've done with temperature-dependent properties. More specifically, I worked with frameworks for visualizing the temperature-dependent yield strength of these HEAs. One can design an alloy with optimal properties for room temperature, but what happens if the metal is exposed to extreme temperatures, such as in hot zones of gas turbine engines? Many properties are a function of temperature, including yield strength, phase stability, ductility, and conductivity. UMAPs are a great tool to portray these changes in a clean and intuitive visual manner. Here we have a t-SNE projection of the estimated yield strength as predicted by the Curtin-Mariska model for temperature-dependent yield strength. This is a dimensionality reduction technique similar to UMAP. However, as we will see, t-SNE does not preserve local and global structure in the data as well as UMAP. Here we see the same space, but projected with UMAP. We see the projection better organizes the composition, placing similar compositions next to each other in the projection. Conclusions from both projections can be made that chromium and molybdenum-rich alloys retain their yield strength at increasing temperatures. Our next course of action was to explore how these UMAPs can aid in the visualization of functionally graded materials. In additive manufacturing, FGMs are useful if you want to print a piece of metal that had multiple properties dependent on its location. For example, in fusion reactors, the inner walls of the reactor core would need to withstand high thermal stresses, while the outer walls would need to be more oxidation resistant. Finding the optimal gradient of compositions to get you from one property to the next seems easy enough. However, there are some compositions that have detrimental properties you want to avoid. Using our UMAP plots, we could better visualize where the deleterious compositions lay while remaining on the best path. The plots below are a great example on better explaining my previous slide. The UMAP on the right preserves the data better, so I will focus on it. Hot cracking coefficient, an important metric in additive manufacturing, is being displayed with its accompanying color gradient. The areas in gray represent the compositions that weren't even feasible because they do not contain a single FCC microstructure. Lastly, the stars represent a binary gradient between cobalt and nickel. This is a simple proof of concept that UMAP projections could be used to visualize compositional gradients in high dimensional spaces. Here we see several examples of linear gradients, all which start at tungsten and end at various compositions within the HEA space. With this tool, we seek to couple such a visualization technique with existing FGM path planning frameworks. Instead of a linear gradient, there's room for improvement to find an optimal path, i.e. the path that upholds the highest properties. Our last area of research consisted of delving into the field of optimization. Edisonian approaches or trial and error design of experiments are not feasible for HEA alloy spaces as they are combinatorially vast. Because of this, we rely on closed loop optimization schemes such as Bayesian optimization. Closed loop meaning we decide the next experiment based on the previous experiments. Bayesian optimization techniques rely on Gaussian processes, Bayesian optimization techniques rely on Gaussian process regressors as surrogate models. As we get more data, the Gaussian process regressor is able to make better prediction on the design space. For the plot to your right, the P ratio is queried with density functional theory, an expensive calculation. The P ratio is then estimated for all other points in the space based on the data thus far. As more points are observed, the regressor effectively learns the space. After many iterations, the framework has learned that niobium has the highest P ratio. Furthermore, the standard deviation of these points are being plotted simultaneously on the bottom GIF. Bayesian optimization takes the prediction and the uncertainty of the prediction to choose the next point to query. Thus, by visualizing these metrics, we can quote, unquote, see the thought process behind the optimization scheme's decisions. Here we are visualizing how the predicted uncertainty associated with a Gaussian process changes in high dimensional compositional space as more points are observed. We see points near known points appear brighter as we are more confident in property predictions. Regions where we haven't measured are darker as we are more uncertain of predictions in those regions. As a summary, we've applied this visualization technique to 3 topics of importance to HEAs: temperature-dependent properties, FGMs in high dimensional compositional spaces, and optimization. There's lots of work to be done in the future given the frameworks we have developed this summer, such as the ones below. The last aspect of my summer research was to develop a blog-style website for additional UMAP findings to be displayed outside of in research papers. The UMAP technology is so versatile that mainly any property can be plotted. That being said, there's lots of information to be shared. In Google Sites, I constructed a simple site that included an introduction/summary to what our work is about, a page to learning more about the members of the research team, and a blog of numerous UMAP and accompanying descriptions. The link to the site can be seen in the comments. These are the citations I used to complete the presentation. And again, thank you to the OREU program at Texas A&M for giving me this opportunity. Thank you to Dr. Ariave and Brent Vela for guiding me and giving me the tools to complete this work. I hope you enjoyed the research presentation as much as I enjoyed completing it. Woo, what an eventful summer. This was my first glimpse into practical engineering work, specifically in the field of academic research. I'm so grateful to have gotten this opportunity to learn and grow. Between collaborating with my peers and mentors, improving my technical skills, and learning what it means to be a high-level research, I have a lot away to take from this internship. Thank you so much.